An extremal surface is defined by the interaction of a vector field and an energy function. At each point x in space, the vector field assigns a direction. Consider the line determined by x and its direction. We restrict the energy function to this line. If x is a local minimum, then it belongs to the extremal surface. Here's a simple way to move a nearby point onto the surface. First, we find its direction, and then we move it to the nearest minimum along its line. We iterate this process until it converges. As an example, we construct a vector field and an energy function based on an input set of surfels. For a point x in space, we weight the input surfels according to their distance from x. We use the weighted average of the surfel directions to assign the direction at x. This defines the vector field. The energy function is the weighted average of the distances from the input surfels to x. We see from these isocontours that there is a valley in the energy function near the input surfels. Together, the energy function and the vector field define the extremal surface. At the surface points, the vector field is tangent to the isocontours of the energy function. The surface normals are not aligned with the vector field. Let's see an example in 3 dimensions. Here's a very sparse set of input surfels. We use the procedure we described to attract points in 3 space onto the surface. To suggest arbitrary starting positions in space, we use a grid of points. In 5 iterations, the whole grid converges onto the extremal surface. Here is the complete surface implied by the input surfels.